Imagine that on the surface of our luminary, which gives life a deep black abyss, suddenly appears. This is not a sunspot and not a random shadow. It is a giant hole in the corona of the sun through which incandescent plasma and invisible solar wind escape into space. Right now, this stream is rushing toward Earth at a speed of millions of kilometers per hour. Is our civilization ready to meet this cosmic threat? Today, we will look into the very heart of the solar hole to understand how the mysterious processes inside the star change our life on Earth forever. For thousands of years, humanity looked at the sky with awe, fear, and boundless hope. For our ancestors, the sun was not just an astronomical object, it was the embodiment of divine will, the source of life, and an unshakable symbol of eternity. In ancient Egypt, the god Ra crossed the sky every day in his golden boat, leading a fierce struggle with darkness. For the Incas, it was Inti, the progenitor of their civilization. In all these cultures, one common idea prevailed. The sun is perfect, unchanging, and pure. The idea that whole spots or any other imperfections could exist on its face seemed not just absurd but blasphemous. Before we begin, write which city you are from so that we know how far our stories fly. And do not forget to subscribe. This philosophical concept of the perfection of celestial bodies was deeply rooted in European thought thanks to the works of Aristotle. The great Greek thinker argued that everything above the moon belongs to the sphere of ether, an unchanging and ideal substance. For almost 2,000 years, this belief was the unshakable foundation of Western science and religion. However, as often happens in human history, the truth began to leak through the cracks in dogmas, and these cracks were first noticed by those who dared to look at the sun not only with the eye of faith, but also with the eye of curiosity. The first documented evidence that the sun has flaws comes from the East. Chinese astronomers, as early as the year 840 before our era, made records of dark spots that appeared on the solar disk. They described them as flying birds, or dark figures slowly crossing the fiery surface. But since these observations did not fit into the European scientific paradigm of the time, they remained unnoticed or were ignored for centuries. A true revolution took place at the beginning of the 17th century when Galileo Galilei, Thomas Harriot, and Christoph Scheiner aimed their newly invented telescopes at the sun. This was a moment of great intellectual upheaval. When Galileo, using the projection method, saw dark spots, he realized that these were not planets passing in front of the star, as some of his contemporaries claimed, trying to save the theory of Aristotelian purity. These were objects located on the surface of the sun itself or directly above it. They appeared changed shape and disappeared, which indicated that our luminary is a dynamic, changing, and perhaps even chaotic place. This discovery was the first step toward the demystification of the sun. It showed that the sun is not a static lantern in the sky, but a physical body subject to the laws of nature that we can study. However, despite this, the scientists of that time still had no idea what these spots actually were, let alone more complex phenomena such as coronal holes. For them, the sun remained a solid or liquid object, perhaps covered with clouds or hot ash. The next big leap in understanding the nature of solar activity occurred only 200 years later. In the year 1859, the English amateur astronomer Richard Carrington witnessed a phenomenon that forever changed our perception of solar-terrestrial connections. While observing a large group of sunspots, he suddenly saw an incredibly bright flash of light that lasted only a few minutes. This was the first recorded solar flare. But the most interesting thing happened 18 hours later. A powerful geomagnetic storm hit the Earth, the strongest in the written history of humanity. Auroras, which are usually observed only near the poles, were so bright that residents of the Caribbean islands could read newspapers in the middle of the night. Telegraph lines around the world began to spark, causing fires and shocking operators. Even with batteries disconnected, telegraph systems continued to operate, powered by energy that literally poured from the sky. Carrington suggested that there was a direct link between the event on the sun and the geomagnetic chaos on Earth. This was the first suspicion that the sun is capable of ejecting matter and energy that can physically affect our planet. In the same period, spectroscopy began to develop a science that allowed scientists to decompose sunlight into colors and see the dark absorption lines discovered by Joseph von Fraunhofer. This made it possible to understand the chemical composition of the sun and reveal that it consists mainly of hydrogen and helium. It was spectral analysis that later became the key to the discovery of the corona, the outer atmosphere of the sun, which could be seen only during total solar eclipses as a silvery halo around the black lunar disk. For a long time, the corona was considered a static shell, but observations became increasingly mysterious. Scientists noticed that the corona extends for millions of kilometers into space and has a temperature hundreds of times higher than the temperature of the surface of the sun itself. This seemed paradoxical. How can the atmosphere be hotter than the heat source? It was like moving away from a fireplace and feeling that it became hotter at the other end of the room than near the fire. In the middle of the 20th century, the young astrophysicist Eugene Parker put forward a revolutionary theory. He suggested that the corona does not just hang around the sun, but constantly expands into outer space, creating a stream of charged particles, which he called the solar wind. His colleagues were initially skeptical of this idea, believing that interplanetary space is an absolute vacuum. However, the beginning of the space age confirmed Parker's correctness. When the first Soviet and American satellites, such as Luna 1 and Mariner 2, went beyond the magnetosphere of the Earth, they recorded a constant flow of plasma moving from the sun. It was established that the solar wind always exists, but its speed and density are constantly changing. And this is where we come to the main mystery of our topic. Where do these flows come from? Why is the solar wind slow in some places and incredibly fast and powerful in others? The answer began to emerge only in the 1970s. The Skylab space station, launched by the National Aeronautics and Space Administration, was equipped with X-ray telescopes that could see the sun as never before. On the resulting images of the corona, scientists saw something strange, a huge, dark, almost black areas where solar matter seemed to be absent. They looked like real failures or holes in the very structure of the solar atmosphere. These areas were called coronal holes. Unlike sunspots, which are cooler areas on the surface known as the photosphere, coronal holes are zones in the corona where the magnetic field lines do not close back on the sun but go far into open space. These are unique open highways through which solar plasma is no longer held by magnetic bonds and can freely escape outward at a colossal speed. Understanding that these holes are sources of high-speed solar wind was a turning point for all of heliophysics. It became clear that the sun is not just a lamp that shines, but a complex magnetic machine that constantly interacts with the environment. And when one of these giant holes is opposite the Earth, our planet falls under direct fire from particles carrying the energy of entire stellar systems. This story of discovery, from the mythical god Ra to the complex images of Skylab, shows us how long we have traveled toward the realization of how vulnerable our place in space is. We have understood that the seemingly calm sun has holes which are windows into its turbulent and dangerous interior. After the Skylab station in the early 70s of the 20th century provided the first clear evidence of the existence of coronal holes, the scientific world was gripped by true excitement. This was not just another discovery in the list of astronomical achievements. It was a fundamental rethinking of how our star interacts with the surrounding space. If previously the solar corona was considered a relatively stable and uniform shell, it now appeared to researchers as a dynamic mosaic of bright active regions and huge dark highways leading to infinity. However, observations from Skylab were only the beginning. Scientists realized that for a full understanding of the nature of these holes in the sun, we need to go beyond the plane of the ecliptic, that imaginary line in which all planets rotate. Almost all of our telescopes and satellites looked at the sun from the equator, but coronal holes form most often and most stably at the poles of our star. To see their true shape and understand their influence, humanity needed to send an apparatus where no one had ever been. Thus was born one of the most ambitious missions in the history of cooperation between the European Space Agency and the National Aeronautics and Space Administration, the Ulysses mission. Launched in October 1990, this spacecraft performed an incredible gravitational maneuver around Jupiter, which allowed it to change the inclination of its orbit and fly directly over the northern and southern poles of the Sun. The results of Ulysses' work became a true scientific revelation. For almost 19 years, this apparatus studied the solar wind at different latitudes. It confirmed that coronal holes at the poles are almost permanent structures that eject plasma flows at a speed reaching 800 kilometers per second. This was twice as fast as the usual solar wind coming from the equatorial regions. Ulysses showed us that the Sun has a complex three-dimensional structure, and its magnetic field works as a giant sprayer where coronal holes act as the most powerful nozzles. In parallel with the Ulysses mission in December 1995, another giant of heliophysics was launched, the Solar and Heliospheric Observatory, known by the abbreviation SOHO. This apparatus was placed at the Lagrange point L, one at a distance of 1.5 million kilometers from Earth, where the gravity of our planet and the Sun are balanced. This allowed SOHO to conduct continuous 24-hour observation of the solar disk without any obstacles. It was thanks to SOHO that scientists were able to document in detail the entire 11-year cycle of solar activity. We saw how coronal holes behave during solar minimum and maximum. It turned out that during minimum, they are usually concentrated at the poles, but when solar activity increases, they begin to migrate to the equator, tearing the corona with their dark presence. When such an equatorial hole turns toward Earth, it becomes like a loaded gun aimed directly at us. During this period, scientists began to conduct clear correlations between the appearance of coronal holes and the state of our technosphere. It became obvious that a hole in the Sun is not just a visual effect in the X-ray spectrum. It is a physical channel through which ultra-fast plasma hits the magnetosphere of Earth. The study of these processes ceased to be only theoretical physics. It became a matter of planetary security. In the 80s and 90s, the world faced the consequences of solar activity several times. The most famous example is March of 1989, when a powerful geomagnetic storm led to a complete blackout in the Canadian province of Quebec. For 9 hours, 6 million people remained without electricity because the solar storm overloaded transformers and knocked out the power grid. Although that specific event was caused by a coronal mass ejection, scientists realized that prolonged flows from large coronal holes could cause no less and sometimes more insidious damage due to their long duration. We have learned to understand that the Sun is the heart of our system, but its breath can be deadly. The creation of the Space Weather Prediction Center by the National Oceanic and Atmospheric Administration of the United States of America was a logical conclusion to this stage of history. Scientists began to monitor the size and position of solar holes, daily predicting the arrival time of the solar wind with an accuracy of an hour. The development of technology at the end of the 20th century made us incredibly vulnerable. Our communication, satellites, global positioning systems, and transcontinental power lines, all of this is under the constant influence of what pours out of coronal holes. We understood, to survive as a digital civilization, we must know everything about the Sun. Every historical mission, every step from Galileo to SOHO, brought us closer to the realization that the Sun is not only a source of light, but also a giant magnetic laboratory where we are only random observers trying to guess the next move of the star. This historical path taught us the main thing. The emptiness that we see in coronal holes is actually a zone of the highest activity. These are places where the magnetic field of the Sun opens, allowing stellar matter to escape into interplanetary space. And what previously seemed like just a dark spot on a photograph is today the main object of attention for thousands of scientists around the world. Moving from a historical sketch to fundamental physics, we find ourselves before one of the most intriguing paradoxes of modern astrophysics. To understand why a hole in the solar corona is such a significant phenomenon, we must first understand the incredible and in many ways contradictory structure of the solar atmosphere itself. The Sun is not a solid object. It is a giant ball of plasma, the fourth state of matter in which atoms are deprived of their electrons, which turns the gas into a superconducting medium, sensitive to the slightest fluctuations of magnetic fields. The first scientific mystery facing us is known as the coronal heating problem. The surface of the sun, which scientists call the photosphere, has a temperature of approximately 5,800 degrees Celsius. According to the laws of thermodynamics, the temperature should fall as one moves away from the heat source, the core of the star. However, in the solar corona, which begins thousands of kilometers above the photosphere, something impossible from the point of view of classical physics happens. The temperature suddenly jumps to 1 million, and in some cases even 3 million degrees Celsius. This is like moving away from the flame of a bonfire by 10 meters and suddenly bursting into incredible heat, which is hundreds of times higher than the temperature of the fire itself. It is in this incandescent and chaotic environment that coronal holes are born. In order to understand the mechanism of their occurrence, we must turn to the data of the Solar Dynamics Observatory, abbreviated as SDO, which the National Aeronautics and Space Administration launched in February 2010. This spacecraft became our eyes capable of seeing the sun in many ranges of ultraviolet radiation simultaneously. When scientists look at the sun through a filter with a wavelength of 171 or 193 angstroms, they see not a flat disk, but a complex structure resembling incandescent lace. The bright loops that we see in these images are closed magnetic field lines. In these regions, the magnetic field lines emerge from the depths of the sun and, arching in a giant arc, return back below the surface. These loops work as giant magnetic traps. They hold the solar plasma, compress it, and heat it to colossal temperatures. That is why these zones look extremely bright on X-ray images. A huge amount of energy and matter is concentrated there. However, coronal holes are the complete opposite of these bright structures. On the images from the Solar Dynamics Observatory, they look like deep black abysses that can cover up to 30% of the solar surface. But it is important to understand, these are not holes in the physical sense where the matter of the sun ends. These are regions of open magnetic lines. Instead of closing back on the surface of the star, these magnetic highways break far into interplanetary space, stretching for billions of kilometers to the very edges of the solar system. Since the magnetic field in these zones does not hold the plasma, the solar matter begins to flow unhindered into space. Imagine a balloon that was suddenly untied. The internal pressure instantly pushes the contents out. A similar process occurs in coronal holes, but on a cosmic scale. Due to the constant outflow of matter, the density of plasma in these zones becomes dozens of times lower than in the surrounding corona. Lower density means fewer collisions between particles, which in turn leads to a decrease in the temperature of this region compared to the bright loops. That is why in the ultraviolet and X-ray spectra, these areas look dark. They simply emit much less energy. The physics behind this phenomenon is described by a branch of science called magnetohydrodynamics. Scientists such as Eugene Parker, whose name the most modern solar probe now bears, prove that this outflow is not static. Coronal holes are the main nozzles of the high-speed solar wind. If the usual slow solar wind moves at a speed of about 400 kilometers per second, then the flows from coronal holes accelerate to 700 or even 800 kilometers per second. This is 2,880,000 kilometers per hour. Why is this important for us on Earth? Because these flows do not dissipate uniformly. Since the sun rotates around its axis in approximately 27 Earth days, a coronal hole works as a giant cosmic sprayer. When such a hole passes through the central meridian of the sun, that is, it is directly opposite our planet, a flow of high-speed protons and electrons is directed directly at us. Scientific journals such as Nature and Science regularly publish research on how these structures change during the 11-year solar cycle. During periods of solar minimum, coronal holes are stable and usually located at the poles. They can exist for many months, constantly feeding the heliosphere. However, as the solar maximum approaches, the magnetic field of the sun becomes increasingly chaotic. Polar holes can disappear, and instead so-called transient coronal holes appear at lower latitudes closer to the solar equator. It is these equatorial holes that are the most dangerous for Earth's infrastructure, since the path of particles from them to our magnetosphere is the shortest and most direct. We must also mention the role of the atmospheric imaging assembly instrument on board the Solar Dynamics Observatory. It takes images of the sun every 12 seconds in 10 different wavelengths. This allows astrophysicists to see how coronal holes breathe, how their boundaries change, and how the process of magnetic reconnection occurs at their edges. Magnetic reconnection is another fundamental process in which magnetic field lines break and connect in a new configuration, releasing a colossal amount of energy. It is this process that can turn a relatively calm plasma outflow into a powerful geoaffective stream. Thus, what we call a hole is actually a window into the deep magnetic structure of our star. This is the place where the internal energy of the sun receives a direct exit into space, ignoring the gravitational and magnetic bonds that hold the rest of the corona. It is a physical bridge between the heart of our planetary system and the atmosphere of Earth. Understanding how these low-density zones form and why they become so stable is the key to predicting space weather for decades to come. We no longer look at the sun as an unchanging circle of light. We see a complex multi-level mechanism where every dark failure has a clear scientific explanation based on the laws of electromagnetism and plasma hydrodynamics. When a flow of plasma leaves the boundaries of a coronal hole, it begins its long journey through the cosmic vacuum covering the distance of 150 million kilometers that separate our luminary from Earth. It is important to understand that interplanetary space, which we often imagine as an absolute void, is actually filled with this invisible but extremely energetic substance. This stream erupting from the hole in the sun does not move in a straight line. Due to the rotation of the sun around its axis, the solar wind curves in space, forming the so-called Archimedean spiral or Parker spiral. This can be compared to a rotating garden sprayer. Although each drop flies straight, the overall flow forms a curved structure that covers planets one after another. Scientific data obtained from the Advanced Composition Explorer spacecraft confirm that the composition of this stellar leak is extremely complex. 95% of it consists of protons, the nuclei of hydrogen atoms, moving at relativistic speeds. The rest is made up of alpha particles, which are helium nuclei, and a small number of heavier ions, such as carbon, nitrogen, and oxygen, deprived of their electrons. All this flow carries within it the frozen magnetic field of the sun, which scientists call the interplanetary magnetic field. When this massive flow of plasma reaches the outskirts of Earth, it encounters our first line of defense, the magnetosphere. The magnetic field of Earth acts as a giant shield, creating a region known as the bow shock. It is here that the speed of the solar wind drops sharply from millions of kilometers per hour to subsonic speeds. Most of the solar wind particles simply bypass our planet, flowing around it like water flows around a stone in a fast stream. However, this protection is not absolute. The interaction between the magnetic field that arrived from the sun and Earth's own field is a critical moment. If the south pole of the interplanetary magnetic field is directed opposite to the north pole of Earth, a phenomenon known as magnetic reconnection occurs. At this moment, the field lines break and connect, forming physical channels through which solar plasma literally pours into the atmosphere of our planet. Particles are directed along the force lines to the magnetic poles, the north and south. Entering the upper layers of the atmosphere, in particular the ionosphere and thermosphere, these high-energy protons and electrons collide with molecules of nitrogen and oxygen. The energy of the collisions turns into light-creating auroras. But behind this beauty lies a serious threat. When the flow from a large coronal hole is prolonged and stable, it can cause a moderate but long-lasting geomagnetic storm. According to the classification of the National Oceanic and Atmospheric Administration, such events are often rated at levels G1 to G3 on a 5-point scale. What does this mean for our technological civilization? First, it is an influence on the ionosphere, which becomes turbulent. Radio waves used for communication over long distances begin to scatter or be absorbed, which leads to interruptions in the operation of shortwave radio and global positioning systems. The error in determining coordinates can increase from a few centimeters to tens of meters, which is critical for automated shipping or aviation. Second, it is a danger for spacecraft. The solar flow creates a surface charging effect on satellites, which can cause short circuits in electronics. Moreover, during prolonged influence of the solar wind from coronal holes, the upper layers of our atmosphere heat up and expand. This increases the air resistance for satellites in low Earth orbits, forcing them to lose speed and literally fall to Earth earlier than planned. A well-known case in February 2022 when the SpaceX company lost 40 Starlink satellites due to relatively weak magnetic activity demonstrated how fragile our presence in orbit is. Scientists pay special attention to so-called geomagnetically induced currents. When the magnetic field of Earth fluctuates under the blows of the solar wind, according to Faraday's law of electromagnetic induction, electric currents arise in long conductors on the surface of the planet. This applies primarily to main power lines and railway tracks. These direct currents can saturate transformer cores, leading to their overheating and failure. On the scale of an entire country, this can cause a cascade power outage, the restoration of which can take weeks or even months. Now we are in the phase of the 25th solar cycle, the activity of which turned out to be much higher than many scientists predicted a few years ago. Official reports from the Space Weather Prediction Center indicate that the number and size of coronal holes on the solar equator are constantly increasing. This means that the shelling of Earth will become more frequent. A leading researcher at the Solar Physics Division of the National Aeronautics and Space Administration noted in a recent interview for Nature Journal that we are entering an era when monitoring coronal holes becomes as important for the economy as the forecast of Earth's hurricanes or tsunamis. We must realize what pours out of the hole in the sun is not just light or heat. It is physical matter of another star, which enters into direct interaction with our home. Every flow of solar wind is a test of strength for our technologies, a reminder that Earth does not exist in a vacuum, but is part of a huge and extremely unstable cosmic environment. The study of these processes with the help of modern observatories allows us to gain precious time preparing defense systems for the moment when the next giant hole on the sun turns toward us. Despite the colossal progress humanity has achieved in studying our star over the last decades, the sun remains one of the most mysterious objects within our sight. Coronal holes, although we already understand their basic nature as zones of open magnetic fields, continue to pose questions to the scientific community for which there are no unambiguous answers yet. One of the most fierce scientific discussions concerns the mechanism of formation of these structures in the dynamic plasma of the sun. Are coronal holes only a passive result of the redistribution of magnetic lines, or do they play an active role in the global breathing of the star? Today, in leading scientific institutions, such as the California Institute of Technology and the Center for Astrophysics of Harvard and the Smithsonian Institution, alternative theories regarding the source of heating of the plasma that erupts from these holes are being considered. The traditional model states that energy is transferred through so-called magnetic reconnection, but more and more scientists are leaning toward the theory of Alfvén waves. Hannes Alfvén, a Nobel Prize laureate, once predicted the existence of a special type of waves in plasma that move along magnetic lines like the vibration of a stretched string. According to this theory, it is these waves that transport colossal energy from the depths of the convective zone of the sun directly into coronal holes, accelerating the solar wind to incredible speeds. If this theory is finally confirmed, it will change our idea of how energy travels inside stars across the entire universe. Another area of active debate is the long-term cyclical nature of the appearance of coronal holes and their influence on global changes on Earth. Over the last 20 years, some scientists, in particular specialists from the Royal Observatory of Belgium, have noticed a strange anomaly. Even when the total number of sunspots decreases, coronal holes can remain extremely active. This gave birth to the theory that we may be entering a period of a grand solar minimum, similar to that observed in the 17th century and called the Maunder minimum. At that time, there were practically no spots on the sun for 70 years, which coincided with the so-called Little Ice Age on Earth. However, modern research published in Science Journal warns against hasty conclusions about a direct link between coronal holes and cooling. There is Henrik Svensmark's hypothesis, which states that the solar wind, which intensifies thanks to coronal holes, modulates the flux of cosmic rays entering our atmosphere. These rays, in turn, supposedly help form clouds in the lower layers of Earth's atmosphere. If this is true, then the holes in the sun literally control the cloud cover over our heads. This is an extremely bold and controversial theory, which is now being tested with the help of the cloud experiment at the European Organization for Nuclear Research. Most scientists remain skeptical, emphasizing that the anthropogenic factor and greenhouse gases have a much greater impact on climate than solar fluctuations. But the very fact of the existence of such a complex connection forces us to follow every flare and every hole on the solar disk more closely. The scientific community is also deeply concerned about the possibility of the occurrence of a so-called superstorm. Although coronal holes usually cause moderate magnetic storms, there are mathematical models showing that under a certain coincidence of circumstances, for example, when the flow from a coronal hole catches up with a previous coronal mass ejection, their energy can be added up. This creates a shockwave effect that can break through Earth's magnetic shield much deeper than usual. In such a scenario, we will face a global collapse of digital systems. The National Academy of Sciences of the United States of America, in its report, estimated the possible losses from such an event at $3 trillion in the first year alone. That is why next-generation missions are now being developed. One of the most ambitious projects is the Daniel K. Inouye Solar Telescope located in Hawaii. It is the largest solar telescope in the world with a mirror diameter of 4 meters. It is capable of seeing details on the surface of the sun the size of 20 kilometers. This is incredible precision considering the distance to the star. Its main task is to examine the very base of coronal holes, the place where magnetic lines break. Scientists hope to see the magnetic roots that feed the solar wind. In addition to ground-based observations, we have great hopes for the Solar Orbiter mission, which the European Space Agency launched in the year 2020. This apparatus does not just look at the sun from afar. It uses the gravity of Venus to gradually raise its orbit, and for the first time in history, obtain clear images of the poles of the sun with high resolution. Since it is at the poles that coronal holes are most permanent, Solar Orbiter will help us understand how the global magnetic field of the star, which is called the solar dynamo, works. This will allow us to predict the appearance of new holes months in advance instead of days as it is now. We also cannot ignore the role of the private sector and new technologies in data processing. The use of neural networks and artificial intelligence allows analyzing gigabytes of X-ray images in real time, detecting the smallest changes in the structure of the corona that the human eye might miss. The Helioswarm project, which is currently being developed by the National Aeronautics and Space Administration, involves the launch of an entire fleet of 9 small satellites that will fly around Earth in the form of a swarm. This will allow us to measure the solar winds simultaneously at many points, creating a 3-dimensional map of the flow pouring out of solar holes. We stand on the threshold of a new era in astrophysics, an era where the sun ceases to be an unpredictable deity for us and becomes an object of precise engineering calculation. Every new theory, even the most non-standard one, brings us closer to the moment when we can say with full confidence that we are ready for any surprises our star prepares. We are learning to live in close proximity to a nuclear reactor of cosmic scales, realizing that the dark spots on its surface are not a sign of disease or the end, but the natural breath of the living universe. We are approaching the most important stage of our research to how humanity plans to protect itself from the invisible threat erupting from solar holes. If the last century was the era of first discoveries, the 21st century becomes the era of precision monitoring and active cosmic defense. One of the most ambitious and technologically complex missions of modern times is the Parker Solar Probe, named after Eugene Parker, who first mathematically substantiated the existence of the solar wind. This apparatus is a true engineering miracle. To withstand temperatures exceeding 1,370 degrees Celsius, it is protected by an 11-centimeter shield made of carbon composite. The task of the Parker Solar Probe is to dive into the corona of the sun itself, flying at a distance of only 6 million kilometers from its surface. This is 7 times closer than any other apparatus in history. Why do we take such risks? The answer lies in the mechanism of acceleration of the solar wind. It is inside coronal holes that magic happens. Plasma, which initially moves slowly, suddenly receives a colossal impulse of energy. Parker must record this moment of birth of the high-speed flow. Data obtained in 2024 and 2025 already indicate that the magnetic fields in coronal holes have a much more complex curly structure than we thought earlier. These bends of magnetic lines, which scientists call switchbacks, may be the very springs that push matter directly to Earth. In parallel with the Parker probe, the European Space Agency is developing the Vigil mission previously called Lagrange. This is a critically important project for planetary security. Scientists plan to place this apparatus at the Lagrange point L5. Why is this so important? Point L5 is at an angle of 60 degrees relative to the Earth's sunline. This allows the apparatus to see the side of the sun that has not yet turned to our planet. Imagine that you are standing around the corner of a house and see an approaching car, earlier than a person on the road. This is exactly what Vigil will do. It will record the appearance of a giant coronal hole 4 or 5 days before it begins shelling Earth with its flow. This will give power engineers, satellite operators, and air traffic controllers precious time to switch systems into a protected mode. No less exciting is the development of ground-based astronomy. The Daniel K. Inouye Solar Telescope, which we already mentioned, uses a unique adaptive optics system. It allows compensating for the turbulence of Earth's atmosphere, making the image as clear as if the telescope were in open space. On the latest images of this instrument, we see the solar surface as a boiling soup of convective cells, each the size of the territory of Ukraine. Scientists hope that with the help of Inouye, we will be able to measure the strength of the magnetic field directly at the base of the coronal hole. If we understand how the energy of the magnetic field is converted into the kinetic energy of particles, we can create the first full-fledged digital model of the sun, a so-called digital twin of our star. The future of research is also inextricably linked with the IMAP mission, the Interstellar Mapping and Acceleration Probe. The launch of this apparatus, planned for the second half of the 20s, will allow us to see how the solar wind erupting from holes interacts with the boundaries of our entire system. This will help understand how the sun protects us from galactic radiation. Coronal holes play the role of regulators of this cosmic shield here. Special attention deserves the integration of artificial intelligence into the monitoring system. The National Aeronautics and Space Administration already uses neural networks to analyze data from the Solar Dynamics Observatory. The problem is that the data stream is more than 1 terabyte per day. A person is physically unable to track every change in magnetic loops. Artificial intelligence is trained to recognize patterns that precede the formation of coronal holes. This allows creating space, weather forecasts with incredible accuracy. We are already moving from a reactive model of behavior, when we simply state the fact of an impact, to a proactive one, when we know about the approach of a storm even before it has left the corona of the sun. But what if we go even further? Hypothetical projects exist for creating magnetic umbrellas in space. These are giant coils made of superconductors that could be placed at the Lagrange point L1. Creating its own magnetic field, such an apparatus could deflect the plasma flow from solar holes, protecting not only Earth, but also future colonies on the Moon and Mars. Since there is no powerful own magnetic field on Mars for future settlers, the study of the coronal holes of the sun will become a matter of life and death, in a literal sense. We live in a unique time. Humanity, for the first time in history, is not just observing the wrath or mercy of its star, but is beginning to understand the internal logic of its processes. Every new mission, every sensor on board the probe is a step toward the sun, ceasing to be a source of fear and becoming an understandable neighbor. The dark holes on its surface are not a sign of chaos, but part of a complex mechanism that we are finally beginning to solve. We are learning to see the invisible and predict the unpredictable, preparing the ground for becoming a true interplanetary civilization capable of withstanding any stellar wind. When we move away from our planet and look at the sun not as a source of heat for picnics, but as one of billions of stars in the Milky Way galaxy, the scale of the true threat and majesty of coronal holes becomes even more obvious. In this block, we must realize that our sun is only one relatively calm actor on the great cosmic arena. But this calmness is illusory. Compared to other stellar systems, the processes occurring inside solar holes are critical for understanding whether life can even exist elsewhere in the universe. Let us pay attention to the closest star to us after the Sun, Proxima Centauri. It is a red dwarf, a class M star, which is significantly smaller and cooler than our luminary. However, its magnetic activity is so aggressive that the holes in its corona and accompanying flares eject radiation flows that are thousands of times higher than solar ones. This poses a philosophical and scientific question to us. Is the stability of our sun an anomaly? Coronal holes on the sun are only a light breath compared to the hurricanes that rain on other stars. But for our fragile digital civilization, even this breath can be fatal. In astrophysics, there is the concept of stellar magnetic activity. Every star is a giant generator where the movement of plasma is converted into magnetic energy. In solar holes, we see how this energy is dumped into space. If we look at magnetars neutron stars with the most powerful magnetic fields in the universe, we will see that their holes are capable of tearing matter at the atomic level at a distance of thousands of kilometers. Our sun looks like a quiet harbor against this background, but it is in this harbor that we have built a world that completely depends on microchips, the thickness of which is measured in nanometers. 1 nanometer is 1 billionth part of a meter. Such microscopic technology is absolutely defenseless before the flows of particles rushing from coronal holes at a speed of 800 kilometers per second. Here, a deep philosophical paradox arises. We are used to considering space empty and cold, but in fact, we live inside the sun. The boundary where the solar wind flowing from coronal holes finally collides with the interstellar medium is called the heliopause. It is at a distance of approximately 18 billion kilometers from us. This means that our entire solar system is a giant bubble inflated by the breath of the sun, and coronal holes are the valves that regulate the pressure inside this bubble. We should look at this through the prism of the so-called Great Filter. This is a hypothesis that tries to explain why we have not yet met other intelligent civilizations. Perhaps one of the reasons is precisely stellar instability. If coronal holes on most stars are too large or too frequent, they can simply blow away the atmosphere from planets located in the habitable zone even before the first multicellular organism appears there. Our Earth has a magnetic shield, but it is not impenetrable. It is like an umbrella during a tropical storm. It helps, but if the wind intensifies, it will simply be torn from your hands. What does this mean for our future? When we say that something pours out of the sun, we mean not just plasma, but the very substance of time and change. Every coronal hole is a reminder that stability is temporary. In scientific circles, discussions continue as to whether the sun can survive a so-called super flare, an event that is thousands of times more powerful than the Carrington event of 1859. If a coronal hole of giant scale were to form on the sun in combination with an active sunspot region, the particle flow could literally burn the ionosphere of Earth, leaving us without protection from hard ultraviolet radiation for long months. Now we stand on the threshold of understanding that we are a Type 1 civilization on the Kardashev scale, which is only beginning to master the energy of its star. But to become full masters of our fate, we must learn not just to observe the holes on the sun, but also to predict their influence with an accuracy of 1 second. This requires humility from us. We are used to thinking that we have conquered nature on Earth, but on the scale of the solar corona, we are only dust. Imagine that the sun is a huge ocean of fire, and coronal holes are deep currents carrying their cold and fast water into the unknown. We are sailors on a small boat called Earth, trying to understand the map of these currents. Every new research, every image in the X-ray spectrum is another line on this map. Our vulnerability is not our weakness. It is a stimulus for development. We study solar holes not because we fear darkness, but because we strive for the light of knowledge that will help us survive in this turbulent cosmic ocean. Concluding this block, we come to the conclusion that a hole in the sun is not just a defect on a photograph. It is an open door into the mystery of stellar evolution. It is the physical embodiment of the link between macrocosm and our everyday technologies. And how we use this knowledge will determine whether we remain a civilization that fears the sky or become a species that has learned to dance in the rhythm of its star. We are approaching the final philosophical and scientific synthesis of our journey. Considering everything we have learned about coronal holes from their magnetic roots to their influence on our satellites, we are forced to change the very paradigm of perception of our star. The sun can no longer be viewed as a static ball of incandescent gas that simply hangs in the void. Modern heliophysics, especially within programs similar to the National Aeronautics and Space Administration project called Living with a Star, the Sun, appears before us as an incredibly complex dynamic and, in a certain sense, living organism. Coronal holes in this metaphor play the role of not just defects but vital organs of breathing or pores. If the photosphere can be compared to skin, the corona is an expanded aura, and coronal holes are open channels through which the star exchanges matter and information with the great cosmos. We do not just observe the sun from afar, we literally live inside its outer atmosphere. Every breath we take, every mobile signal, every second of our biosphere's existence takes place in an environment that is formed and constantly modulated by what pours out of these solar rifts. This concept of a solar ecosystem fundamentally changes our understanding of planetary security. Scientists from the European Space Agency, in their latest analytical reports, emphasize that humanity has reached the level of technological development where we have become part of the electromagnetic biosphere of Earth. Our power grids, cables on the ocean floor, constellations of Starlink satellites and space stations, all of this creates a nervous system of civilization which is extremely sensitive to the mood of the sun. When a large coronal hole turns to us, it is not just an astronomical event. It is a direct impact on the nerve endings of our digital world. We must realize the scale of this dependence. Imagine 8 billion people whose daily survival, from the logistics of food products to the work of hospitals, depends on the stability of the flow of particles moving at a speed of 800 kilometers per second. If earlier solar activity influenced only the beauty of the night sky today, it determines the viability of our financial and infrastructural systems. In Nature Astronomy Journal, an article was recently published where the authors argue, our future as an interplanetary species depends on whether we can turn our knowledge of solar holes into a full-fledged system of cosmic immunity. This immunity includes not only telescopes, but also a change in the very logic of building our technologies. We are learning to create transformers resistant to induced currents and developing satellites that can automatically close their eyes during solar storms. But there is a deeper aspect. The study of coronal holes forces us to reflect on our role in the universe. We are the first form of life known to us that is capable not just of feeling the influence of its star, but also of understanding the physics of the processes occurring in its core and corona. This imposes a colossal responsibility on us. We stand on the threshold of the time when the space weather forecast for 120 hours ahead will be just as common and important as the temperature forecast for tomorrow. But behind these figures and graphs lies a majestic picture. We are a part of a great cosmic dance of energy and matter. The sun gives us life, and its holes test our capacity for survival and intellectual growth. Every flow of solar wind is a message from the star written in the language of plasma and magnetic fields. And our mission is to learn to read this message fluently. Summing up the philosophical result of this culmination, we see that man is not a random grain of sand in the cosmos. We are observers who give the universe the opportunity to realize itself. When we look at the dark abyss of a coronal hole on the images of the Solar Dynamics Observatory, we see not emptiness. We see the source of power that shaped our system billions of years ago and continues to shape it today. This awareness gives us not fear, but a deep sense of belonging to something infinitely larger than ourselves. Our star is our home, our engine, and our greatest challenge. And what pours out of its holes ultimately helps us become who we are meant to be, a true cosmic civilization. Our journey to the very heart of the solar corona is coming to an end, but our life under the watch of this majestic star is only beginning with a new page of awareness. We began this narrative with a disturbing question about a hole in the sun that threatens our world, and we end it with the understanding that this hole is an integral part of the breathing of the universe. What pours out of the coronal rifts is not a curse, but a physical reminder that we are not isolated on our small planet. We are children of the star, we feed on its light, but we must also learn to withstand its storms. Over the last 2 hours, we have traveled a path billions of years long, from ancient myths about the god Ra to the ultra-modern sensors of the Parker probe, which right now, as you watch this video, is flying through incandescent plasma at a speed of hundreds of thousands of kilometers per hour. We saw how magnetic lines breaking on the surface of the sun become highways for the solar wind, and how this wind reaching Earth creates simultaneously both the incredible beauty of auroras and the deadly threat to our power grid. Scientific data from the National Aeronautics and Space Administration and the European Space Agency clearly indicate that the 25th solar cycle in which we are now is a time of special trial for our civilization. The number and size of coronal holes will only increase in the coming years. However, today, unlike the times of the Carrington event in 1859, we have knowledge. We have eyes in space and a mind capable of turning the chaos of plasma into precise mathematical models. Every second of this video was dedicated to one goal: to show you that science is not something distant and abstract. It happens right now over your heads in every stream of protons that hits our atmosphere. And although space may seem hostile, it is our true home. The study of solar holes is not only about physics, it is about our responsibility as a species for preserving our technological cradle and preparing for the exit beyond its limits. We call on each of you not to stop at what you have seen. Space is an infinite book, and we have just turned only one page of it. Subscribe to our channel so as not to miss the next deep dives into the mysteries of the universe. Like this video, if you now look at the sun differently than before, write in the comments which part of our research impressed you the most, whether it was the incredible speed of the solar wind or the philosophical vulnerability of our digital world. Remember, the darkness in the corona of the sun is not emptiness, it is a window to knowledge. We are the first civilization that has learned to look into this window without fear. Thank you for spending these 120 minutes with us. Together, we continue to study what makes us part of a great cosmic whole. See you in the next episodes, where we will reveal even more mysteries that the boundless and beautiful cosmos hides from us. Take care of yourselves, take care of our planet, and always look up, because it is there among the stars that our true future lies.